So, hello everybody. Welcome in the new year. I hope you had a good start of it. So now we restart with the lecture. Do you remember what we did before Christmas? There was something about interactions, right? So, this is the point where I wanted to restart today to speak about the interaction operator that we introduced in order to approach the inclusion of particle interactions into KFT in a perturbative way. That was the goal. And let me just write down again where we arrived, and then we'll see what we do from here. So first of all, we said we introduce another source field K into the generating functional, which will allow us to replace specific interaction terms by an interaction operator acting on the generating functional. And it looked like before, right? So looked exactly like before, except that now this additional source field K is acting on the trajectories. So the trajectories were now looking like Green's function times the initial position plus Green's function acting on the source field K. And K was unspecified. It has the only purpose for functional derivatives to act on it so that we can ultimately replace the K by the actual interaction terms that will be contained in the interaction operator. That was the first step. Then we saw that we can include the particle interactions by writing an exponential interacting operator in front of the generating functional, such as to restore the actual interactions. And then, as usual, once the interaction operator has been applied, to set K to 0. And this would be the generating functional including particle interactions. And then if we want to calculate statistics of density fluctuations, for example, we would apply further density operators to that complete expression here. Okay, so this would be generating functional without a 0, and then only of the source field J. Okay, that was the formal procedure, and we saw that we can write this interaction operator in a simple way. It is an integral over d1, but I specified what I mean with that. I'll repeat this. Response field operator of -1, potential of 1, and density operator of 1. Okay. Now, what did we mean by this shorthand notation? We said that we want to understand under any index n as an argument for a function, the combination of wave vector with this index and the time argument with this index. And if you change the sign, so if you write -n as an argument, you mean -kn and plus tn. This is just for notation. And then, of course, we need to specify what we mean by the response field operator. Response field operator of some index s is ks times. Now, functional derivative with respect to the momentum component of the source field K, and it is the momentum component only because of Hamilton's equations. Right? The force term is acting on the time derivative of the momentum. It's a derivative with respect to Kpi, so the component, the momentum component of the source field K for particle I at time Ts. And this is multiplied with the density operator, same particle index here, and the same index for the wave vector. Okay. This was quite important. So ultimately, this derivative with respect to K appears in the exponential. We saw before that derivatives appearing in an exponential create a shift. So this will create a shift of the source field K by a certain amount, and this amount is given by this quantity here. So this will replace, this density operator will be replaced by an actual expression for the density. We will have an expression for the density here times the wave vector, and the wave vector corresponds to the gradient of the potential here. So it's all pretty intuitive what we have found here. All right, that was approximately the situation where we arrived at, and that's what I wanted to restart now. And of course, what we now will have to do will be, first of all, to apply the response field operator actually to the generating functional and see what it does. And then I wanted to go through an example to work out actual terms of perturbation theory. Not to scare you off, but just to show what happens. Okay. Good. Another important thing that we pointed out before Christmas was that if you now apply with a certain number of density operators, or apply a certain number of density operators to the complete generating functional, you see that there will now be a combination of density operators that you have applied and density operators that the interaction term will apply. So we wanted to enter into perturbation theory in a systematic way, saying that now we are going to expand this exponential operator into a Taylor series. So 1 plus I Si minus a half Si squared, and so on. And then, of course, if you stick to first order perturbation theory, you stop the series here, then you will apply a single interaction operator of this form to the generating functional. This single interaction operator will contain two density operators. So for example, and this is the example I want to go through later, if you wanted to calculate a two-point function, that is a power spectrum, with perturbations or with interactions at first order of perturbation theory, you will have to apply 4 density operators. And you know what these density operators do. They will just replace J by an L. And since you can commute the operation of the response field operator here as a derivative with respect to K, and the action of the density operators, which are derivatives with respect to J, you can first apply all the density operators in a row and then see what the response field operator restricted to this expression does to the resulting generating function. Looks pretty easy. Creates lots and lots of terms. But we'll see about that. Okay. So sticking to first order theory, we will have the following problem. First order perturbation theory. we have the problem of calculating an nth order power spectrum. We usually call a power spectrum would be n equals 2. And you want to be in mth order of the particle interactions. You will have n plus 2m density. Should be a bit more specific. Interactions. You will have 2m plus n density operators applied. So this means your generating function will be shifted by a shift tensor containing 2m plus n k vectors. All right, and then we will have to apply response field operators of this sort. All right, so suppose you have already done that. Then you will have a free generating function where now J is replaced by suitable L. And there's still the source field K in the interaction term. So this will look like that. It's the usual integral over the initial conditions. And then e to the power of I, L times x bar of K. So that's where we are. And now we need to apply the response field operator. All right, what will it do? Suppose we pick out one of these factors here. I think we already introduced this notation with a small b before Christmas. This section only. And this makes sense, of course, because we need to split off the density operators. So now we have small b response field operators bi of s, rho I of s. Now I need to look only into the action of the small b operators. Okay, so let me specify this a little bit more. Ultimately, I will have to apply a sequence of mth order interactions. I will have to apply a sequence of m response field operators of this sort, and I will specify the particle indices that are attached to these response field operators as J1 to Jm. Now let me pick out one of them. Let me pick out one of them and see what it does. This is what I have to carry out. Now let's see what, let's say, the response field operator BJS with a wave vector S will do to Z0 of L and K. Again, right? We split off the densities from the response field operators. We get the small, the response field operator with a small b. We apply all the density operators. They will create a shift. Now we will have to finally apply the response field operators there. And now picking, this is what I need to do in total. Now I take one representative example for that. All right, what do we need to do? We need to do a functional derivative with respect to Kp(Js). So this will bring down the argument of the exponential. Then we will have to take the functional derivative of the argument with respect to K. So we will get the unchanged exponential, and now times I ks here times delta x bar of k derived with respect to k p j s at time ts. All right. Now you see that if you take the functional derivative of the x bar of k with respect to k, only the second term will respond. You will retain an integral over Green's function, but there will be no dependence on the initial particle positions anymore. So this means that the factor that you create in this way does not depend on the initial phase space anymore. So you can pull this out of the integral. And what remains will be the free generating functional, because afterwards we set k to 0. So all that this response field operator does will be to multiply the free generating functional with some term, the response field factor. So that's pretty nice. So now it has lost its hat, right, because it has lost its function as an operator. And what will remain is just the set 0 of L, and you know what set 0 of L is, right? Like in mathematics, right? Once you arrive at a point that you have already seen, you say the problem is solved. So all we need is these factors here. And then, of course, each of these factors, or each of these, where is it? Yeah, each of these response field operators will create another one of these factors, and then you just have to multiply them. Okay. I just noticed that this is wrong, right? Let me do this again. Sorry. All right, again. We need to have the following thing. Times this. That's what was wrong, right? We need to retain the scalar product with a L. And this is going to be the response factor. Okay, now, what is this? Okay. Good. Now, what is this? This factor is going to be now going to specify these time arguments. That's what happens. So you take a functional derivative with respect to a Kp field. So this means that where you had K before, you just have a 0, 1 here because you have taken the P derivative. You took the Kpjs derivative. This is why we only pick out particle Js here. Then we took this derivative at the time Ts. That's why we have a delta function here. And now I need to take into account that this scalar product here between the shift tensor L and the rest contains a time integral. That's how it was defined. And I want to use time argument T prime for the time that I have to integrate over here. So I'm calling this the time argument that I'm integrating over here, T double prime. And therefore, I have to take the delta function of T double prime with minus Ts here. Okay, good. Now, this is straightforward to calculate. All right, that's going to pick out the second row, the second column of the Green's function. This is going to fix T double prime to Ts. So what you get is what we call the Hamiltonian propagator of T prime and Ts. Here we just have 1 and this is taken for particle Js. We close the bracket here. Okay, and you also know what L is, right? Once you have applied all these density operators, you know that L is minus the sum over Ks times 1, 0 times. Now that we want to integrate over T prime, I need to say T prime here, T prime minus Ts. And the total number of density operators is L. So these are the shift tensors here. This is the shift tensor L here. So if I insert this here, I get minus IKS times the sum. Now, of course, and I forgot to say that all of these things apply to particle J. So, yeah, I need to multiply this with a unit vector at index J. All right. So what do we have? First of all, as I said, this is an integral over T prime. Of this integral over T prime, this delta function picks out only the Tj. So this will replace the T prime by Tj here for all the contributions here. Then we will have to multiply this vector there, Gh in the position component and the 1 in the momentum component, with a 1, 0, and of course this will pick out the Gh only in the sense of a scalar product. We'll have to multiply this Ks out front with the Kj's we have in here. So all that remains is this expression here. Now times the scalar product of Ej with Ejs. So this will give you a Kronecker delta J, Js. So these are the response factors. Okay, what happens here is quite intuitive. First of all, you only get a contribution if Ts precedes Tj. Right? The Tj's are the times when the final density operators or the density operators contained in interaction terms are later than the times Ts here. This is for causality. Because if you take the Hamiltonian propagator here, and the second argument would be later than the first argument, this would be excluded by causality. So this response field operator can only be positive, can only be non-zero for Ts less or equal than Tj. Then another important fact is that each of these response field factors identifies two particles with each other through the Kronecker delta. Very important for evaluating this later. And then you have this the scalar product here of the k vectors. Remember that this represents the gradient of the potential. This k vector in the response field represents the gradient of the potential that describes the force. And this is multiplied with a wave vector of density fluctuation mode. And if the two are orthogonal to each other, in other words, if you have a density fluctuation going this way, and you want to know, so you have a density fluctuation mode going this way, all the way to u, and you take gradient of that perpendicular to its wave number, it's going to be 0. Because there is no change in the density perpendicular to the direction of the density fluctuation mode. So all of that makes perfect sense, and now we have evaluated the response field factors, and now we know everything that we wanted to know. Right? These are the response field factors. We know what the free generating functional is after inserting the shift tenses here. So now we can proceed. Do you have any questions? Is anything mysterious of what I'm doing here? I think the essence is pretty clear. Right? We have identified an interaction operator that allows us to pull particle interactions from the generating functional, leaving a free generating functional over. This interaction operator is exponential, so we can expand it into a Taylor series, which gives rise to systematic ordering of perturbation terms. If you know this already from quantum field theory, you know that the individual terms in this exponential series can be represented by Feynman diagrams. And of course, just to keep order in the perturbation terms, we will later also introduce a kind of diagram for the perturbation terms that will occur. At first order, we just act with the interaction operator on the generating functional. Interaction operator contains two density operators, in addition to the density operators that describe what we want to know. So we'll have a sequence of density operators applied, which will replace the J source field in the generating function by the shift tensor L. And ultimately, we will need to apply this kind of response field factors. Then we will be done. Remember one thing: the interaction operator contains an integral over times and wave vectors. Remember, we had this expression for the density operator. There's still an integral left over the times and the wave vectors that are contained in the interaction operator. So this would mean that once we have worked out these response field factors, you would have to integrate over Ks, and we would have to integrate over Ts in the allowed range. Right? So with Ts moving from 0 to Tj, but not further. All right? You were about to show up, but no. All right. Yeah, Hannes.
I mean, this pattern is stuff, right? So there's only one term surviving.
There's only one term surviving. You just don't know which.
Yeah. And then
right? Because you can't identify this one.
The age of TJS as the TJS.
Doesn't need to be. We will see about that. Warren is shaking his head because he did this in his bachelor thesis. I'm leaving it in this way because otherwise you're very likely to be confused later on. But let's see it. Let's have a look at an example and yeah, this will be fine. All right. There is more to say, but I will do this as we go through the example. What's the simplest example? Let's take a 2-point function with with first order perturbation theory. It can't be simpler than that. Okay, let's have a look at that. And the more complicated problems will then be part of the problem sheets, of course. So, example. Let's have n equals 2. So we want to have a power spectrum. Let's have m equals 1. So we want to have first order in the interactions. This means that we will have to apply 2m plus n equals 4 density operators. And this means you know in principle what the shift tensor is going to look like. It's just going to be a sum of 4 terms, k1, k2, k3, k4. But that's a waste of notation because we know already very much more about the k vectors. So we have a set of wave vectors first of all. Now what do they look like? Well, we start from a homogeneous random field. And this means there is one delta function. Remember that? There's one delta function preceding our generating functional, which says that the sum of all these wave vectors must be 0. Okay? So we know that the sum of these 4 must be 0, so they are not independent. And we know one more thing, right? The k3 and k4, which I want to use in order to describe the wave vectors contained in the density operators, which are part of the interaction operator. They must be equal in size but opposite in sign to each other, right? As this integral says. There's one wave vector here that is negative here. So we know, first of all, that k3 is minus k4. Lovely. So these two add up to 0 as well. So these two must add up to 0 individually. So we only have 2 wave vectors, in fact, to distinguish, right? And I can write them as k1 minus k1, k1 prime minus k1 prime, if I take the liberty to give a prime to the wave vectors that are internal, in the sense that they appear in the interaction operators, but not in the density operators that you yourself apply. So you provide the external k vectors by what you want to know, and there are the internal wave vectors contributed by the interaction operator. All right. this is something we know. And now we have to choose particle indices. And now comes the problem of assigning the JS to the S. So, how do we do that? That's what we need. Now we know that each of these response fields will connect two particles with each other. We know from the propagator here that we can only connect response field vectors identified by the J's here. No, identified by the JS or the S here, with wave vectors that are later than them. Now, if I take the indices 3 and 4 for the wave vectors describing the particle interactions, I need to attach, or I need to identify J4 or J3. We still have to select that with one of these, right? Because they describe density operators applied later. And this is what causality demands. It doesn't make sense to identify J3 and J4 because they would give a propagator that is 0, right? They cannot contribute. So I need to either do this, identify these two, or that. Yes. Or that. Or this. Or that. But then you see that the response field, in fact, comes with a negative sign. So this is the negative wave vector here. So this rules out all the connections that come from here. So we have only the choice to identify J4 with J1 or J4 with J2. Well, that is manageable. So we could say, for example, if I start enumerating now with 1, 2, 3, this is one choice, right, where J4 is identified with J1. Or I could do this, where J4 is identified with J2. These are the only choices left over by causality and by this notation here, which has the negative wave vector assigned to the response field. Okay, so these are the JS's that we need to apply. If I now focus on the first choice and then leave the rest to you, then this JJS will identify wave vector number 4 and here wave vector number 1. And so this gives rise to the response field factor minus I. Now the S is the 4th wave vector here. So this is minus K1 prime. Then I have the only wave vector that is identified with this one. That's the K1. And we have propagator going from T1 prime to T1. That's the response field factor I would get from there. Let's do the same again for this configuration here, because you look pretty puzzled. understand your puzzlement very well. Now, if you look at this configuration here, and I start again with a minus I here, now I have Ks. But the wave vector corresponding to the response field is always this one here, is minus K1. Minus K1 prime. Now, this scheme here identifies this wave vector, or this particle index with a second one. But the second of these wave vectors is minus K1. And the propagator remains the same. So you see, the response field factors are just plus or minus this expression for these two cases here. Indeed. All right, so these are the response field factors for the situation that we are looking at. Do you want a break? Some of you look pretty tired. Do you want to move a bit? All right, then move a bit. I will have to clean the board anyway. Fünf Minuten oder so. All right, can we restart? I think now it's time for a diagram. Right? It will be much less confusing once you see the diagram. Okay, here are the rules. This is the generating functional. Yeah, don't laugh, right? This is standard notation for statistical physics. Okay, along the circumference of the circle, time is running, and time equals now is this, and everything below that is before that time, and we need to respect time ordering, as you saw. So any kind of interaction must be before that. So, for example, here. Now we want to have a two-point function, so we attach two wave vectors to that. Usually in these kind of diagrams in statistical physics, these arrows signify functional derivatives. And this is exactly what we are doing, right? Because the k vectors are all produced by functional derivatives with respect to j, which gives rise to those. Yeah, with respect to j everywhere. Okay, so this will be wave vectors k1, k2. All right. So this signals the order of the perturbation. The order of the power spectrum or the correlation function that we want to have. Now, as we saw, any interaction term or any interaction factor adds another two wave vectors, and they get a prime. K1 prime. I could, of course, write. Yeah, let me do that. K2 prime. Now we know more, right? We know that this is minus K1 prime by definition of the interaction operator. And this is minus K1 by homogeneity of our random field. Right? So the external wave vectors must add up to 0 individually, because the internal wave vectors add up to 0 by definition. Okay, good. Now, as we said, any response field will identify two particles, and we denote this identification with a dashed circle, a dashed circle segment. And it must start here, right? Because it must start at a response field, and the response field gets the negative wave vector just by our definition of the interaction operator. Now, the dashed line that goes from here must connect to any wave vector later because of causality. Right? The interaction cannot act backward in time. Connecting it to this one would be possible, but would result in a zero term, because the propagator is 0. So it must proceed somewhere here, for example, this wave vector. But it could also go, I don't want to write it in the same diagram, right, because then it's getting really confusing. It could also go here, but since these two wave vectors are symmetric to each other, so the terms that we get are symmetric under exchange of K1 and K2, the only other possibility must be physically equivalent to that I've written down. Okay? Mm-hmm. No. I mean, ultimately, we are integrating over at least the internal wave vectors, so they can attain all directions you want. So no, there is no meaning to that. Okay. And now we have to represent all these wave vectors here with particles. Right? So we need to assign particles to them. For example, 1, 2, 3. Now this dashed line identifies 1 and this one. So this will be particle 1 again. And that's the configuration that I wrote down previously, right? So remember, one of these sets that we wrote down was this one, and that's exactly this configuration. We could do otherwise, right? Could start again. I could connect my response field to the other one. K1 minus K1, K1 prime minus K1 prime. Okay, and now if I go through this enumeration again, I have 1, 2, 3, 2. And that's the other configuration we wrote down previously. Okay, so that's the scheme, right? You start with a circle, you attach as many wave vectors as you need. You draw the response lines that are possible, and then you identify accordingly. Just for the fun of it, what would happen for a 2-point function with interaction at second order? It's a 2-point function, so we have 2 external wave vectors, which of course must also satisfy K1 plus K2 equals 0, so K2 is minus K1. Now I have 2 interactions to take into account. It could look like this, right? So we would have K1 prime minus K1 prime, K2 prime minus K2 prime. Give them arrows even though they have no meaning. Okay, now what response lines could we draw? And we could go from here to there. We could go from here to there, but then we couldn't contribute 0, it makes no sense. We could go from here to there, because by our notation of times, right, this is an interaction later than that one. So that precedes this one, so this can act on this one. So going from here to there would be possible, going from here to there would be possible, going from here to there, or from here to there. Going from here to there would not be possible. Right? That would go back in time and be forbidden by law. Okay, and then of course from here, you could still go here or there. You cannot start here, right? Because any response field factor must start at the negative vector, according to our definition of the interaction operator. Okay, so let's take one of these possibilities and start here. God damn it. So we could do this, right? That would be one possibility for second order perturbation theory applied to a 2-point function. Now we can take 1, 2, 3. Now this is connected to 1. This would be 4. And this is connected to 3. So this would be 3 again. Okay? So we would have 6 particles to distribute in a scheme saying 1, 2, 3, 1, 4, 3. And this would define the response field factors that you have to apply. Clear? Yes.
So do I understand right that for every order of perturbation we draw one more dotted arrow?
Yes. Because this interaction term contains one response field, and the response field identifies 2 particles, and the dashed lines are there to indicate which particles you identify.
Are we still calling this a Feynman diagram, or is this?
No, I wouldn't call this a Feynman diagram.
I wouldn't either. I just wasn't sure what the nomenclature.
No, it's just a diagram to illustrate the perturbation term. And as I said, right, this notation of taking the generating function in the middle, signaling or indicating functional derivatives by arrows and so on, this is standard in statistical physics. And you find this everywhere. It's not my particular invention.
Yeah, so you mentioned you have this diagram -1.
Yeah.
The arrow was for a big one, second one was K1. So that I'm confused. Does it have to go to -3?
It has to start at the negative wave vector of a response of an interaction term.
Yeah, but where does it have to be? The loop of where
It can go anywhere. It can go to any later wave vector. Right? So it could go to K1, it could go to K2. In this case, it can also go to these 2 here. It just has to start here or here. And then it can go to any later wave vector.
So it doesn't matter which.
It doesn't matter which you choose for the target. It does matter which you choose for the root point. This is not a law of nature, right? It's just a matter of our convention. You could start here as well, but then you would have to attach a minus sign here, which doesn't matter, and we just have to stick to some kind of notation. All right. So that's the scheme. Now let's continue to work with this configuration here, corresponding to this diagram. As I said, this one must be physically equivalent. So if you want, work this out and see whether you get the same term. All right. So these are the JS here. Now the next thing we need is the shift tensor, the components of the shift tensor. So we have these, and here the JS, of course, appear again. Yes. Yes.
So it's just like a very arbitrary convention, but you always start with negative.
Yeah, that's exactly true. You choose the sign convention, but then stick to it. That's like with the Minkowski metric, right? Of course, you're free to choose between minus plus 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 and or plus minus minus minus, but don't confuse them. All right. Now, remember that we introduced earlier LQ and LP components. And I would like to identify them again. And we did them in a let's say, less intuitive way by identifying those parts of L that multiply the initial position Q, or the initial position of the particle, and the vector that multiplies the initial momentum of the particle. So I want to write this scalar product here in this way. This is the goal. This is how I identify the LQ and LP components. And now I'm going to use that I think we call this X0 here. This was this vector here. And now you see that if you go through with that and you perform the time integration that is part of the scalar product, you take account of this delta function here, then you find that LQ is minus the sum of Ks. And then the component LQJ, so the component LQ for the particle number J is given by this expression here. Because you multiply this out, and you say these are for all the particles J times Vj. And then if you multiply these two expressions, you get the delta J, Js again. So these are the LQs here. And the LPs just have a time, where are we? A time attached to them. Okay, so these are the shiftings, and of course we need them in order to work out the generating functional, free generating functional. So we need these two things. Now let me write down what they look like in this specific case here. So in our case we have 4 wave vectors, like the diagram shows. So I could simply start with minus K1 times delta J, J1, and so on and so forth. So let's do that. Minus K1 let me write down LQ2. Right? So the particle index is 2. There is only one index Js that equals to 2. And it's in position number 2. So this would just be minus K2, K2 times not times. We are done. We are done because there's only one contribution. So it's minus K2. So it's plus K1. All right, this is one example. Now we need, in order to work out all the contributions to the conservation terms. We need all of them. So let me start with LQ1 now. So J is 1. Now we have two JS that are equal to 1. They are in positions 1 and 4. Now remember, the K vectors are K1 minus K1, K1 prime minus K1 prime. So I get a minus K1 and a minus K1 prime. Okay, because of this identification here. All right, LQ2 we already had. LQ3, now there is only one contribution to LQ3, which is K1 prime. So we get that. All right. And of course, now we have LP1 is minus T1 K1 plus T1 prime. K1 prime. Remember that T1 prime must always be less or equal than T1. And we have LP2 is T1 K1 and LP3 is minus T1 prime K1 prime. Okay. How do you get them? First of all, if you go back to this diagram here, you see that K1 is combined with minus K1 prime. So you just sum these up, right? K1 minus K1 prime. Take the negative because the negative sign is part of the definition of the shift tensor. So the first LQ is just minus K1 plus K1 prime. The second is just minus K2 or plus K1. The third is minus K1 prime. So in this way, going through this diagram, you can simply assemble these LQs in this way. All right. Now what do we do with them? Remember, ultimately we want to have a power spectrum. But we already have an expression for the power spectrum. Remember we said the final generating functional, free generating functional for a certain shift tensor L can be factorized. Right? And I'm now alluding to a result that we had earlier, some normalization factor that I now don't care about. There's a sequence of integrals over prime wave numbers as we introduced them there. And then we have a product of contributions that were all standardized. Right? I'm alluding to the fact that we already proved that the free generating functional can be factorized. And remember, we could factorize it at the expense of introducing additional wave numbers. You remember how many we needed? Right? We said if I have a total of L density operators applied, I will have L times L minus 1 divided by 2 wave vectors in total. Yeah. So in our case, L equals 3, because the response field identifies 2 particles. We have 2 wave vectors applied. Sorry, we have 4 density operators applied. But of these 4 density operators, we know that 2 are identified by a response field, so 3 remain free. So L equals 3. So we need in total 3 combinations. And we said that we will have L minus 1 times L minus 2 divided by 2 internal wave vectors that we denote with primes. So with L equals 3, we will have 1 by 2 divided by 2. We will have 1 prime wave vector only. Okay, now I'm alluding to the result that we had when we factorized the generating functional. This was LQJ. Now in our case, I will only have one internal wave number, which will be the K32 prime. And this will be LQJ minus K32. Confusing not only you, but also myself. We will have wave vectors K21, K31, and K32. And according to that recipe that we derived there and that you find in the lecture note, this is LQ2 minus K32. This is LQ3 plus K32, and this is K32 prime. You remember that, right? The factorization of the generating functional. Now evaluate it for L equals 3. And so there are 3 by 2 divided by 2. There are 3 different wave vectors we need in total. And there is 1 additional wave vector. And these 3 wave vectors look like this. All right, now we can evaluate these 3 factors here. So in our case, this free generating functional is the normalization term. Now there is a single integral over K32. And now we have I21, I31, I32 to integrate over. And the i's are the generic factors that we worked out in the factorization of the free generating function. Okay. I'm going to write them up. IJK is first of all, a delta contribution. And then a contribution, which we call the free nonlinear power spectrum, curly P here. Now this has LPJ, LPK, KJK as arguments. And finally, what was this? Do you remember that? A1 and A2 functions are the momentum correlation functions that we derive. They're just integrals over power spectra. This is the parallel projector with respect to the vector R. Okay, yes. So we know what to do when we want to evaluate this. So now we have everything in a form that can be directly worked out. Right? We have all the wave vectors that we need to insert into these factors. We have the LP contribution. And we know how to identify the LQs or the LPs with the wave vectors that we have. Okay, so let's do that. Let's do that. So we have to evaluate integral over K32 I21 times I31 times I32, and each of these i's is a sum of a delta and a curly P. So we get terms that only contain delta functions. We get terms that contain only one curly P factor. We get terms that contain two P factors, and we get terms that contain three P factors. So we can order them in a sequence of curly P's. Now the first thing that we get is the delta functions only. That's 2 pi to the 9th power. Delta D K21 times K31 times K32. And you see, since you are integrating over K32, this is just going to go away. That's going to be a factor of 1. And what remains are delta functions that set K21 to 0 and that set K31 to 0. So K32 is already 0, right? Because we have integrated over this delta function. So then LQ2 would be 0, and LQ3 would be 0 as well. I'll wipe them off, of course. This means that the response field factors that you would get for these configurations are all 0. So this does not contribute. And so the result of inserting this expression into the further calculations is 0. And if you work this through, so let's not go on with that. Then you get 2 pi to the 6th power. And now you get a sum of delta D of K31, delta D of K32, now curly P of LP2, LP1, K21. That's the first term you get. Then you get a delta D of K21, delta D of K32, curly P of LP3, LP1, K31. That's the next one. And you get this one. These are the terms that are linear in the curly P. And please feel free to go on. Now, how do we continue? Here you see in the first term a delta function with K32. You can integrate over this directly. This will replace all K32s by zeros. Do we have any K32s? Well, there are these shift vectors LP2 and LP1. Remember we had this here, and the LPs likewise. Right? All right. So there's a K32 and K21. This will be set to 0. So the third argument of this curly P will just be an LQ2. And the LQ2 is given by a K1. So if I work out the first term, I get integral K32, 2 pi to the power of 6, delta D K31. The delta D K32 is gone if we carry out this integration. And this integration will reduce the 2 pi to the 2 pi to the power of 3. And then we will have curly P of LP2, LP1. And as we said, right, K21 is LQ2 because K32 is 0. But you know all these things, right? You know the LQs, you know the LPs. So you also know what K31 is. Let's see. This is LQ3 plus 0. All right. Now let's insert these terms. So we have curly P of LP2. That's T1 K1. We have LP1. This is minus T1 K1 plus T1 prime K1 prime. And we have K21, which is LQ2, and LQ2 is K1. And now we are done, right? Now we can insert directly these arguments into this equation here. Ask the computer to work this out, and you get this factor here. But then we have an LQ3 out front, delta of LQ3, and the LQ3 is minus K1 prime. So this delta function sets the K1 prime to 0. But we need the K1 prime in the response field factor. So this does not contribute. Aha. Okay, then move on to the next, and to the next, and so on. And of course, this is all excessively boring and strains your patience to the rest. So, no. We did something else. We wrote some code to create a diagram. This is no witchcraft. So you know how to set up the diagram. Once you have a diagram, everything is fixed because the generating function is factorized. So you can work out these curly p's here once and for all, hopefully. But the configuration of wave vectors that you need in order for mth order perturbation theory applied to an nth order correlation function is a completely deterministic machinery. So you ask the computer to make these diagrams, you ask the computer to set up the wave vector configurations that are necessary in order to evaluate these diagrams, and you let the computer run. And there's one PhD student in our group who has brought this to some mastery. He has now advanced to 8th order perturbation theory, which is quite remarkable. Now, what we have looked at here is 1st order perturbation theory. And you see what happens. Yes. The main reason why I wanted to show this to you is to explain how you can systematically arrange for perturbation theory in KFT. Very important to know. Very important how to do this systematically. But don't ever do this yourself. I mean, except on the next problem sheet. The probability that you mess up signs, terms, and so on is very quickly approaching 1. And the number of terms that you have to evaluate is very quickly approaching infinity. Let this do the computer. And it does it quite well. And as you said, as I said, we advanced to 8th order perturbation theory, also with the help of Boran here. And that's a major advance, and that allows us to apply perturbation theory in this one. Okay, that's what I wanted to show you, just for you to know, not for you to practice that. All right, this was also the reason why I wanted to show this factorization of the generating functional. I don't know quite well for what else exactly it could be useful for, but it is very useful for perturbation theory and for the computer to work this out. Okay, that's what I wanted to say about perturbation theory. Next time I wanted to show you some examples for results of perturbation theory. So you see what the 8 orders are looking like. There are several exciting properties of that, of the results, I mean, not of the calculation. But you'll see about that. There's one more thing I wanted to say. Laura Polzer over here has volunteered to help me with the lecture notes, which I greatly appreciate. Nonetheless, it will take her some time, of course, to get used to that. So there will be a short break in my delivery of the lecture notes. So please be patient. It's going to come. Next thing, over Christmas, since I was lacking other things to do, I wrote a Jupyter notebook with which you can do some calculations on your own if you wish to do so. I will put this on, make this available on the web page, and then you can play with all these things. And you will very quickly find out that numerical integration of exactly the curly p function here is a very delicate thing to do, but nonetheless, play yourself. Okay, so much for today. Do we have any questions to address before we leave? See you next week.